Hello everyone! This video is for my final project for the ECE 432 Advanced Computer Vision, and it is a literature survey on traditional approaches to texture analysis. As we know, the traditional approaches are usually full of formulas, but don't worry, this talk will not relate to any formulas, so it's a formula-free talk. So, first, before I start, I have to give you a few background knowledges. First, what is texture? According to Portilla and Simoncelli's definition, texture is an imagery that is spatially homogeneous and usually contains repeated elements, often with random variations in position, orientation, and color. For example, look at the three pictures under the text. The first two are textures, and the third one, the avocado, is not texture. Then, what is texture analysis? It's to extract meaningful features for classifying and quantifying the texture properties. In a word, it's to distinguish the textures with others. How to do that? Actually, for traditional approaches, we have statistical, structural, and model-based methods. And the texture analysis can be used for medical imagery classification, material retrieval, and texture modeling, etc. So the goal of this talk is to focus on traditional texture analysis method, so CNN-based methods are not included, and compare their efficiency, strengths, and weakness. On this page, we can see there are so many different methods to do texture analysis. For statistical method, we have first-order statistics, gray level, co-occurrence matrix, local binary pattern, autocorrelations, and gray level round length matrix. For structural ones, we have primitive-based methods, taxon theory, and edge detection. Model-based methods, we have Markov random fields, fractal analysis, 2D autoregression, mosaic model, Boolean model, and transform-based models. First category, the statistical method. The key idea is to analyze pixel intensity relationships without assuming explicit texture primitives. So it studies the pixels. For first order, it's very simple. It only starts the one pixel at once. So, for example, the histograms, we use the histograms to count the number of different pixels of different intensity, and then we get the mean, variance, and entropy of these histograms to get the features. Second order, it studies 2 pixels at one time. Actually, it counts the number of 2 adjacent neighbors appear together, like the gray level co-occurrence matrix. And for higher order, it studies the round length matrix, local binary patterns, etc. The round length matrix is studies the longest round in the imagery. So it usually related to several pixels together with the same intensity. It's called a round. Local binary pattern, for the original local binary pattern, it studies 8 neighbors of the central pixel, and for extended local binary pattern, it can study further neighbors. For example, now I give you a gray imagery of size 4x4. For the gray level co-occurrence matrix, we study 2 adjacent neighbors that appear together, like the 2 and 4 in red color. We found in the 0-degree direction, the horizontal direction, there is only one pair of 2 and 4. or 4 and 2, whatever, and then we put 1 at 2, 4 in the matrix and 1 at 4, 2. So it's symmetric. And for the round length matrix, it's simpler. The round length matrix, for example, we define the 45 degrees, so it's a diagonal round, and we found there is only one round shown in the blue line of length 2, and it's for intensity 1. So we found 1, that's for the intensity, the first row, it's for the intensity 1, and length 2, the second length. So we put 1 at 1, 2. For the local binary pattern, for example, we have the smaller 3 by 3 gray image block, and we get the central intensity is 2. Then we set all the neighbors which has greater intensity or equal to the central pixel at 1. And for others, set 0. Then we get the local binary pattern. But it's too much because we have 8 different numbers, but that's binary numbers. Here, from the 1, 1, 0, 1, 1, 0, 1, 0, in the counterclockwise direction, we form an 8-bit binary number, and then we get 218. That's how we represent the local binary pattern. Here I show you some examples. Actually, that's an experiment to study the different ways of texture analysis. First, we get 2 textures, the blue bricks and the yellow fabric. And then we get the grayscale images. And first, we use the first order statistics to count the histogram. And I have 3 more features, that's mean, variance, and entropy. For the second one, I use the gray level co-occurrence matrix to analyze the image in the 0 degree direction, and I get some highlight spots. That's where the most frequent neighbor pairs appear together. And then by analyzing the GLCM, I get a few different features like the contrast, correlation, variance, entropy, and these features can help us to distinguish the 2 textures. For the local binary pattern, it's easier. First, we compute the local binary pattern. It looks like the original grayscale images, and then we analyze the digitals. Actually, we analyze the 8-bit binary numbers and get a histogram for them with 3 more extra features, mean, variance, and entropy to distinguish the 2 textures. Those textures that look similar usually had similar features in the histogram. So we can conclude that statistical methods are simple, widely used, and computational efficient. However, they have limitations in capturing global spatial relationships, and they are sensitive to scaling and rotation. To improve that, people propose rotation invariant local binary pattern is to rotate the local binary pattern until they found the smallest binary number. And the uniform local binary pattern, it defines a texture that is uniform, usually have less than 2 bit changes in the circle binary number, and then if the texture is not uniform, just set a small number for that. So it reduces the dimension of the local binary pattern. And local Gabor pattern is a combination of local binary pattern with Gabor filters, which I will introduce later. The second category is the structural method. The key idea is to decompose textures into primitives like text tones or edges and model their spatial relationships. Text tones, proposed by Jules, is a basic perceptual units, or we call it primitives, in pre-attentive human perception. And if we study the text tones from a linguistic perspective, it's like a bag of words, and those text tones compose the textual language. Edge detection. Here I list several famous edge detection methods like Sobel, Roberts, Brevis, Kenny, and LOG. The structural methods, they are very simple and they can model spatial co-occurrence of texture primitives instead of pixels. However, they work best for well-structured textures like bricks and fabric, as I shown before, but less effective for stochastic textures like clouds and grass. So here I also show an experiment to show the texture structural of the method of the texture analysis. It's named perceptual bulb. It's a convex color homogeneous region with shape and color attributes as I extract on the textures, and it is represented as probability density function of shape. You can see the small text tones extracted from the textures. And then finally we have the model-based method. It's a big category, and the common things for the model-based methods is that they assume a generative model for textures. For example, the Markov random fields, it usually models dependencies between the neighboring pixels, and the 2D autoregression model, it assumes the intensity of the central pixel is a linear combination of an order of upper and left neighbors plus noise. That's the original version, and that's a causal one. For non-causal one, it can also depend on the right and lower, what is the future pixels. Fractal pixel. Fractal analysis based on fractal model, it has two key features or parameters. One captures the self-similarity and the other captures the roughness of the texture. The mosaic and Boolean models, they share one thing in that they assume a Poisson process in texture generation, and the generation is related to small primitives like lines, triangles, circles, polygons. But for the Boolean model, it allows overlapping of the random primitives, and it usually has overlapping things. But the mosaic model is a partition-based. It divides the texture into small partitions, so there's no overlap for mosaic model. Finally, the transform-based model, like Fourier transform, wavelet, curvelet, ridgelet, and Gabor filters. Those transform-based models are widely used in DSP, and they can also be used for texture analysis. They assume that the textures can be decomposed to different sine, cosine functions in 2D, or different filters in 2D, or the wavelet mother functions. Here I show an experiment to use 2D autoregression to analyze the textures. That's a two-order analysis, so we can see all of them have two-order neighbors. And we can compare the two textures using their feature maps. So the advantage of model-based methods are they are theoretically sound and interpretable. However, they are computationally expensive and hard to estimate the parameters. It usually requires the iterative computation of those parameters. And here I list a table to compare texture analysis methods. The statistical method like grade level co-occurrence matrix, local binary pattern, and grade level round length matrix, they are efficient but less accurate and less robust. Structural methods, they are not so efficient and not so accurate and not robust at all because they cannot deal with irregular textures. Model-based methods like Markov random field, 2D autoregression, fractal model, Boolean model, they are not efficient at all, but they can improve the accuracy and they are robust. To be noted, the hybrid method, like the energy variation, I can explain the energy variation is a combination of grade level co-occurrence matrix and local binary pattern and edge detection method and compute their energies as their features. And the local Gabor pattern, as shown in this picture, it can analyze the textures with different frequencies and in different orientations from 0, 45, 90, 135, like that. And they are more efficient than model-based methods, and they are accurate and they are very robust. For the challenges of these texture analysis methods, the first one is we have to achieve the scale and rotation invariance because many traditional approaches are not robust to transformations like local binary pattern, GLCM, like that. And the second thing is that we have to select the features. Sometimes we get hundreds of thousands of features and we have to reduce those too many features. So it's a problem how to select most meaningful features. And efficiency accuracy trade-off, we have to pursue the trade-off. Like the model-based methods, they are accurate but costly. We have to solve that. And finally, the interpretability. Because we haven't covered the CNN-based method here, obviously CNN-based methods, they can improve the accuracy and efficiency by training, but the CNN-based methods are not explicitly interpretable. We don't know what happened, we just apply several layers of convolution and then get the results. We have to know what happens. For future work, I think using vision language models like CLIP to extract the semantic-based features is promising because it can align the extract features with the natural texture attributes like coarseness, contrast, glossiness, scale, like that. Okay, for the takeaways, we know the statistical methods are simple and effective. Structural methods are interpretable but struggle with irregular textures. Model-based methods and the transform-based methods, they are theoretically sound but computationally expensive. Finally, the most important one, hybrid approaches often provide better performance, which aligns with the idea of boosting. Thank you.